Have you ever looked at a giant factory, a huge chemical plant, and just wondered, how does it all work? How does it know when a tank is full or a valve is open? Well, it all comes down to a constant, high-speed conversation happening between thousands of different parts. So today, we're going to pull back the curtain and see how these industrial machines actually sense the world and talk to each other, especially when a single mistake could be a very big deal.
All right, let's just jump right into the deep end with a really critical question. I mean, it's pretty obvious that electronics and, say, explosive gas are a terrible mix, right? One tiny spark and it's catastrophic. So how on earth do you put a sensitive electronic sensor right in the middle of all that danger to see what's going on? It sounds impossible, but engineers have solved this problem in a super clever way.
So here's our game plan. We're going to start our journey right in the danger zone, talking about these spark-proof sensors. Then we'll look at how machines can measure more than just a simple on or off. After that, we'll see how all that data gets to the system's brain, and finally, we'll zoom out to see how the whole thing gets connected together.
Okay, first things first, let's set the scene. Just picture a part of a factory where the air is filled with explosive gas, or maybe a fine dust, or even tiny fibers. This is what's called a hazardous area. You absolutely need to know what's happening in there, but you can't just, stick any old piece of electronics inside. The whole system has to be designed for safety from the ground up.
The whole strategy here is basically separation. You see on the left, you've got the sensor living right there in the hazardous area. And way over on the right, tucked away in a safe room, is the PLC, the control system. But that little box in the middle, the intrinsic safety barrier, that is the key to the whole operation. Think of it like a bouncer at a club for electricity. It makes absolutely sure that only a tiny, safe, pre-approved amount of power ever gets past it and into that danger zone.
And that, of course, brings us to the hero of this part of our story, the special kind of sensor that's designed to live behind that safety barrier. This isn't just any sensor. It's built to a very specific standard to be inherently or intrinsically safe.
And this is it, the NAMR sensor. Now, NAMR is a German standard for devices that are intrinsically safe. And I love that term, right? Because it means safety isn't some feature that was added on later. It's built into its very nature. It's baked right into its DNA. Its whole purpose is to run on such a tiny amount of energy that it's physically incapable of creating a spark hot enough to cause an explosion. So, how does it pull that off? Well, the entire design is about limiting energy. It runs on a super low voltage, just 8.2 volts, and it has this specific internal resistance. Now check this out. When the sensor detects something, it doesn't shout a big on signal. No, it just subtly changes its own resistance, which causes a teensy-weensy change in the electrical current flowing through it.
And when I say the current is tiny, I mean it is tiny. We're talking about a maximum of 5 milliamps. That is an incredibly small trickle of electrical energy, nowhere near powerful enough to create a dangerous spark. So that's the whole secret, right there. By strictly limiting the voltage and the current, the system absolutely guarantees safety. It's just physics.
Okay, so the NAMR sensor is fantastic for a simple yes or no question. Is something there, or is it not? But what if you need more detail? What if you need to know the exact pressure in a pipe or the precise temperature of a liquid? For that kind of information, we have to go beyond simple on and off signals.
And this really gets to the heart of the difference between digital and analog signals. A digital signal is like a basic light switch. It's either on or it's off, 1 or 0, that's it. But an analog signal, now that's your dimmer dial. It can be off, it can be fully on, or it can be any of the infinite shades of gray in between. It gives you that rich, detailed, continuous stream of information.
Now, to read these more nuanced, continuous signals, you use a device called a transmitter. What it does is it measures a real-world property, like pressure, and it translates that into an electrical signal. That signal then travels to a special analog input module on the PLC, which is specifically built to understand this kind of detailed information.
And the language that these analog devices all agree to speak is a current, not a voltage. The industry-wide standard is a 4 to 20 milliamp signal. So think of it like this. 4 milliamps could mean the absolute minimum value, like 0 pressure, and 20 milliamps represents the absolute maximum pressure. Every single value in between corresponds to a specific reading. It's a simple, super reliable, and universal language for all these industrial sensors.
Okay, so we've got this smooth, flowing analog signal, this 4 to 20 milliamp current making its way to the PLC. But here's the catch. The PLC is a digital brain. It thinks in cold, hard numbers. So how does it translate that subtle analog feeling into a number it can actually use to make a decision?
Well, the moment that analog signal hits the PLC, it gets converted into a number. That number is then immediately stored in a specific memory location inside the PLC. This location has its own unique address, called a peripheral input word, or PIW. The easiest way to think about it is like a mailbox. Each sensor has its own unique mailbox where it delivers its data, so the PLC program always knows exactly where to go to find the latest update.
Now, to really understand how that number gets stored, we just need to take a quick peek under the hood at the fundamental building blocks of all digital information. But don't worry, I promise, it's way simpler than it looks.
Everything, and I mean everything, starts with the bit. It is the most basic unit of data there is. It's just a 0 or a 1, off or on, yes or no. That's it. Every complex piece of information you've ever seen on a screen is just built from massive combinations of these simple little switches.
So the PLC groups these simple bits together to represent more complex ideas. You can see here that a group of 16 bits is called a word, and that is exactly what our PIW, our little mailbox, is made of. The key takeaway here is that by just stacking these simple ones and zeros, the PLC can create any number it needs to perfectly represent a real-world temperature or pressure, and then it can use that number to make a decision, like opening a valve or maybe sounding an alarm.
So, we've gone from a single sensor all the way into the data inside the PLC's brain. Now, let's zoom out one last time, because a modern factory doesn't just have one PLC and one sensor. It has hundreds, maybe even thousands of them. So how do they all talk to each other and work together as one giant, coordinated system? At the most basic level, it starts with physical wires. This is the nervous system of the machine, with each individual wire carrying one signal from one sensor directly to a terminal on the PLC. And look, for a single machine or a small, self-contained area, this works perfectly fine. But it gets completely out of hand, a real nightmare when you try to scale it up to an entire factory.
You can just imagine the mess of wires. So the solution is to build an industrial network. The best way to think about it is like a data superhighway. Instead of thousands of little backroads, these protocols like Profibus and Profinet create a single high-speed communication loop that everything can connect to, kind of like the computer network in your office.
But to get all the data onto that highway, each remote station, each little group of sensors needs an on-ramp. And that on-ramp is a device called an interface module, or an IM. It acts like a translator or a local manager. It gathers up all the data from its local team of sensors, bundles it all together, and then sends it out over the network to the main PLC. And critically, each IM has its own unique address, so the main PLC always knows exactly which station it's hearing from. So we've basically seen how a single nerve ending, the sensor, sends a signal that travels all the way up the nervous system to a local brain, the PLC. But modern automation doesn't stop there, which leaves us with one final thought to chew on. If a single sensor is a nerve ending and the PLC is a brain, what happens when you connect hundreds or even thousands of these brains together across an entire company? Well, that's where you get the foundation of the smart factory, of Industry 4.0, and that's a whole other story.